Welcome to a new tutorial from DIERS International. In this video, we will introduce you to the results pages of a dynamic foot pressure measurement with the DIERS pedogate system. Mind that the total number of provided parameters in this examination type is quite high. Thus fasten your seatbelts, there will be a lot to discuss. DIERS pedogate is part of the further development of the classic DIERS pedoline product line. Unlike the smaller portable pressure plates of the DIERS pedoscan series, the platform for DIERS pedogate is stationary and integrated into a treadmill. This combines both ups and downs. Among the advantages is the size of the platform. With a length of 100 cm, it is able to accommodate 2 consecutive footprints. In a treadmill situation where your patient is walking on the spot, the system is thus capable of recording an endless sequence of steps. Furthermore, the hardware integration of the platform into the treadmill allows for the dedicated derivation of the real walking speed, along with the deceleration and acceleration forces that affect it. Due to these forces, the set treadmill speed can sometimes vary by up to 10%. The complete integration of the platform into the treadmill prevents the distortion of the pressure data. A possible downside is the treadmill situation, which can influence the gait behavior of your patient, depending on his treadmill experience, by changing the coordinative requirements. On the one hand, the spatial movement changes when the floor becomes punctum fixum, the patient punctum mobile. Normally, it is the other way around. Walking on the spot also eliminates the air resistance that our movement on solid ground is geared toward. Thus, we often see compensatory signs such as an increased trunk inclination, a shortened stride length toward the end of the swing phase, and a compensatory increase in stride frequency. To bring the gait pattern closer to the natural habitus, allow your patient a few minutes to get used to the new situation before the first measurement. For this purpose, you may ask your patient for putting his fingertips on the handrail. This will help your patient gain spatial orientation. Inform your patient that his steps are too short and ask him to take slightly longer steps. This usually leads to an approximate neutralization of the step length. Observe your patient walking on solid ground. This gait pattern should be the reference for the treadmill situation. When the patient shows a smooth and harmonious gait pattern, the fingertips can slowly be released again and the arms can be set in motion. As soon as the arms swing in rhythm with the stride and the gait is not characterized exclusively by acceleration and deceleration phases, the recording can be started. The calculated result data should now reflect the habitual gait perfectly well. Back to pedobarography. The acquisition of foot rollover in dynamics is an absolutely critical component of the analysis of gait behavior and function. The progression of the COP line in relation with the resulting ground reaction force is key to understanding functional processes, interactions, and compensations. DIERS pedogate combines this function with the ability to determine step-related parameters such as cadences, step lengths, or track widths. Furthermore, as part of the DIERS 4D Motion Lab, the module is used as a synchronizing unit that puts the data from 4D motion and leg axis into a time-synchronous context. In DICAM software versions 3.19 and later, gait and walking analysis are set to uniform starting point, which is set to the initial contact of the left foot in each measured sample. This data is transferred from the pressure plate and allows for an optimal comparability of your recordings. Please note that the data acquisition now takes a little longer than the known 5 seconds. In order to guarantee a 5-second result in any case, starting with the first left contact, we have extended the pure recording time to 7 seconds. This allows the analysis of the foot pressure measurement to find the first initial contact as a starting point, advance from there the usual 5 seconds to the end point, and pass this time frame to the other modalities. With DIERS pedogate, we are moving deeply into clinical gait analysis, extending the module's utility when used as a component in the DIERS 4D Motion Lab and DIERS High Performance Lab systems as a clock generator and measurement modality in its own right. As in all other modalities, the Summary Results tab is used for a detailed overview of the recording result. On the left side of the user interface, all recorded stance phases are initially displayed. Depending on the number of recorded steps, the display is larger or smaller. The stance phase highlighted in gray shows the respective side-related average step. The determination of this mean representative is based on the consideration of the pressure distribution in all recorded data as well as the course of the COP for each recorded step. The imprint that comes closest to the resulting mean value in this observation is determined as this very representative. Note that the less variance is measurable in the recorded pressure data, the more stable the selection becomes. A single, strongly deviating step can cause a distortion of the mean values with a usually small number of total steps. If this distortion is then closer to the deviation than to the mean of the remaining steps, the outlier may get selected as a representative, which can possibly be a hindrance when interpreting the data. It is best to ensure that your patient's gait pattern is stable on the treadmill prior to the data acquisition. This guarantees for a representative compilation of roll-offs. The graphs and values shown on the results page refer to the sequence of registered footprints, starting with the first recorded rollover. The complete sequence can be played via the video control in the blue header bar. The display of footprints and force curves then shows the respective footprint in the sequence. This is then outlined in yellow on the left-hand side. In the upper area of the user interface, the impression of the step pair is displayed based on different calculations. The average matrix shows the average vertical force applied to the sensors under load between the initial contact and the end of the pre-swing. The higher this average value is, either by short-term very high force or by constant force loading, the more pronounced this area moves towards the red zone representation, following a color sequence ranking from blue for low pressure to light blue, dark green, light green to yellow, orange and a red for maximum pressure. For example, the lack of control of a sufficient forefoot drop in the loading response, as can occur with dorsiflexor weakness, would cause the forefoot to drop to the ground quickly after initial contact so that it would exert pressure on the platform over a large portion of the ground contact. By extending the contact time, the average pressure attributed to the forefoot will increase and possibly have a higher pressure value relatively to the midfoot. Thus, the forefoot would show up in red. In the maximum display, the maximum pressure value is output for all sensors under load, regardless of the time at which this occurred. This is particularly interesting when pressure peaks on the sole of the foot are to be identified. Think of a diabetic foot or an uncontrolled heel contact that severely increases the total eccentric demand during the loading response. So, while the average matrix follows a more time-bound context, then rather dilutes short-term pressure peaks, the representation maximum turns the focus towards the maxima regardless of the duration of the occurrence and the time sequence. So, there are advantages as well as disadvantages in both views. In order to meet these more neutrally, the third representation, the forced time integral, is suitable. In principle, each loaded sensor delivers 100 values per second, which provide information about its load. In order to evaluate pressure peaks neither too strongly nor too diluted, the integral, which is the area below the sensor individual force curve, can be used. A forefoot weakness would then be displayed somewhat wider in red in the forefoot, since not only the contact duration, as in the average matrix, is taken into account. The pressure peak with which the forefoot briefly hits the ground is also given somewhat more weighting in this way. The forced time integral thus offers a more neutral view of the pressure distribution, and it is therefore the first port of call for most users for an initial representative impression of the pressure conditions during the rollover. In the lower section of the interface, the total pressure is shown on the left and the total force is shown on the right. A brief explanation of the recording of force via a pressure platform. Technically speaking, a pressure plate does also record force. However, contrary to the function of the sensors in a force plate, these sensors are only able to register vertically running force vectors. On the other hand, this design and function allows a disproportionately higher sensor density, so that this vertical force can be recorded over the entire sole of the foot and thus becomes visible as pressure map or vertical force distribution. So, If you were to compare the ground reaction force curves of a force plate, they would be somewhat higher since horizontal forces are quantified in addition to the vertical force. However, the characteristic shape of a force curve remains unaffected. From a technical point of view, therefore, in a pressure platform the pressure is at the same level as the force, since both parameters can only record the vertical components of the force development anyway. The difference in these two values lies in their respective scaling. The total pressure indicates the force exerted in relation to the area of the contacting sole of the foot in Newton per square centimeter. An initial contact with the heel and a foot in physiological dorsiflexion initially applies the weight to the ground over a small area. The associated force value in Newton per square centimeter is correspondingly high. However, if contact is made as a foot flat, with a non-physiologically lowered forefoot, just as much weight would hit the platform, but over a significantly larger area of support. The corresponding force value in Newton per square centimeter is then significantly lower. On the right side, the total force is displayed, as it adds up over time over all loaded sensors. There is no calculation on the area and thus provides a similar information value as a force platform would do. In these diagrams you can see the force curves of the current steps in red on the left and blue on the right. The light gray area behind represents the standard deviation for all steps taken. The dark gray graph is the mean force curve for the respective data set. The gait phases belonging to the stance phase can be read relatively easily from a force curve. So the curve starts with a small tick representing the initial contact. Since the actual load transfer does not begin until after this point, the deflection initially decreases again a little. This is due to the initiation of the physiological heel eversion and the soft heel cushion that initially transmits the force. From this short moment on, however, the force curve begins to rise analogously to the load transfer. In the rising section, the body is in bilateral support. Increasing load creates torques in the joints that are controlled primarily by eccentric muscle activity of the dorsiflexors and knee and hip extensors in the sagittal, hip abductors in the frontal, and knee external rotators in the transverse. This is the central functional task in the so-called loading response, the phase we are currently focusing on. The moment of the maximum force is also the moment of maximum eccentric demands on the aforementioned structures. A large number of gait deviations become visible here. At the same time, this moment is the end of the loading response and the transition into the single leg support phase, which begins with the universally known mid-stance. In mid-stance, the ground reaction force decreases. This is made possible by a large support surface, as the foot has already fully lowered to the ground, and a forward moment that automatically tilts the tibia ventrally. The muscular input required for this is vanishingly small, hence the decrease in force values. Through the tibial forward movement, the heel pressure slowly begins to release and transitions to a concentric activation of the plantar flexus. This is the change from mid to terminal stance and is equivalent to the moment when the mid-bottom of the force curve has been passed. From this moment on, the force curve experiences its second rise, caused by the increasing contraction of the plantar flexus, which reaches its concentric maximum at the end of the phase with the second maximum of the force curve. Did you know that at this point the force development of the plantar flexus increases to a level of 85% of their maximum voluntary contraction capacity? This is also the cornerstone of a wide range of gait deviations, as in today's sedentary lifestyle we often see a tendency for the retrotibial muscles to weaken. At the time of maximum force, the contralateral foot hits the ground, the single support ends and moves over to pre-swing. Here, successive load transfer occurs to the contralateral foot and the force curve decreases to zero by the end of the contralateral loading response. In a pressure platform, the peaks at the end of loading response and terminal stance can be expected to reach the same level. If you observe a significant difference between first and second peak, we come to the question of whether the higher peak shoots up too high or the lower one representing an insufficiency. In the vast majority of cases, you can simply refer to the y-axis of the graph and define the peak that is closer to the real body weight of your patient as the neutral one. If the other peak is higher or lower, you can derive increased or lower activity. Also, the lowering in the middle of the graph should not present itself too much off the body weight. A lowering to less than 60% of the body weight can be observed, for example, on a medial collapse pattern. On the right side of the screen, you can see the sequence of steps as a pressure distribution image of the pressure plate grid, as well as the course of the center of pressure, or COP for short, as a red dot under the left foot and a blue one under the right. Because of the playback frequency of the video display, a detailed interpretation of the rollover process is hardly possible here, since one can only vaguely perceive the specific deviations at this point. If the displayed color subdivision does not allow you to differentiate sufficiently, for example, if everything tends to be colored blue, simply drag the slider under the footprint images further to the left. In this way, you reduce the display threshold so that less stressed foot zones are also highlighted somewhat better. However, you also approximate the borders between the color gradations in this way. In the Results tab roll motion, the focus is once again directed to the ground reaction forces in relation to the occurrence during the rollover. At the top, there are 3 impressions for each foot, which show the foot at 3 critical points in time during ground contact. For both sides, the footprint at the end of the loading response is shown on the left. Usually, the maximum pressure is still on the heel and the forefoot is already in contact, but only to the extent that this zone usually shows a blue metatarsal area, but the toes have not yet been lowered. A dorsiflexor weakness would already load the forefoot significantly higher at this stage, so it tends to appear more green, yellow, or even red. A forefoot walker would have the entire heel area missing at this stage. In mid-stance, the foot is shown at the end of the mid-stance phase. The body's center of gravity is relatively centered over the support surface at this moment, so the pressure appears fairly evenly distributed. The pressure under the heel has decreased significantly compared to the left image and has moved accordingly towards the forefoot. Thus, at least the hallux should now also show up in the pressure map, albeit not overly loaded. The position of the relative pressure maximum in the area of the anterior transverse arch gives you good information about the direction in which the force transmission is developing. If the red zone is centered below the 4th or 3rd ray, it can be assumed that the direction of force in the subsequent terminus stance is in the direction of gait. If the red zone is now already below the 1st metatarsal, the forward force vector tends to lead in the diagonal to medial. In order to maintain the gait direction in this position, part of the released force in terminus stance must be used to perform a directional correction. That part of force necessary to correction prevents the full focus of force into locomotion. The gait pattern shows tendencies of insufficiency. In the push-off phase shown on the right, the end of terminus stance is visualized. The moment occurs just before the contralateral foot touches down. The heel should no longer be loaded at this point. The maximum pressure on the forefoot continues to be under the center of the anterior transverse arch, tending to be slightly more medially aligned. Insufficient plantar flexors would prevent the heel from coming off the ground. If the retrotibial muscles appear rather hyperactive, forefoot pressure is primarily found already in the area of the toes or hallux. Lateral segments of the anterior transverse arch are then already off the ground. When playing the video, the foot changes over time. The currently displayed pressure curve always refers to the foot outlined in yellow in the left area. As the feet are positioned above the underlying ground reaction force, they also correspond approximately to their temporal occurrence in the roll-off process. Thus, the footprint for load response can also be seen above the first vertical dividing line in the force curve, which indicates the end of that very phase. The mid-stance is located quite centrally over the gap between the 2 peaks, and the pre-swing phase is located on top of the second vertical dividing line. Once the data is played as a video, a yellow index line indicates the timestamp in the video. The graph changes display with each occurring step. The respective force curve always matches the yellow outlined impression on the left side. Due to this somewhat wider scaling compared to the similar display on the first result page, the course of the ground reaction force can possibly be viewed in somewhat more detail. At the bottom, the complete time course with all measured steps is displayed as a ground reaction force graph. Here it can be seen relatively quickly how reproducible the foot-ground interaction is from one step to the next, or whether a deviation that was noticed in one step can be repeated over several steps. If it is a one-time outlier, it is better to ignore it. In the 2D/3D view, only the pair of feet with the grey background on the left are initially displayed enlarged side by default. Click on the video control play to play the rollover process and repeat it as long as the video is running. There is no automatic change from one step to the next. The footprints with the grey background are the representatives for the individual rollover and are closest possible to the mean step, which is represented as a real ground contact that represents the average rollover process in the best possible way. So the right-left arrangement does not necessarily have to be 2 consecutive steps. If, for whatever reason, you would like to see a different step, simply click on the desired footprint in the left image. By default, all result pages display the footprint as an interpolated graphic. However, there are other visualization options on this page. Change the display to a representation of the grid of the sensors actually loaded. You can also view the pressure data of the index matrix in 3D instead of 2-dimensionally. This separates pressure areas not only in terms of color, but also spatially. To the right, you can set the graphic to a standard view that you prefer. You can also select an individual view by moving the mouse pointer into the index matrix and holding down the left mouse button. If you now drag the mouse up or down, the print page will rotate vertically around the horizontal axis. If you drag the mouse sideways, the image rotates horizontally around the vertical axis. Dragging the mouse sideways while holding down the Alt key will rotate the image around its center axis. The slowed down but continuous playback of the rollover via the play control in connection with the COP line shows you exactly how the body weight is carried over the floor, which foot zones bear the main load, and which foot zones are relieved. In a dynamic sequence of movements, even a slowed down sequence is still difficult to interpret. Therefore, the simple playback of a video may be sufficient to be used to gain an impression of the gait behavior. If more detailed information about the spatiotemporal sequence is required, it may be useful to switch from frame to frame manually. To do this, use the plus and minus symbols in the video control, or more simply, the right and left arrow keys on your keyboard. This way, no gait deviation will remain hidden from you. However, in order to determine an anomaly, we should understand what an expected pressure curve should look like. Here, the progression of the black COP line is particularly noteworthy. Let's recall back to the static foot pressure measurement. The center of pressure combines the pressure distribution of a foot under one point. It is thus the point towards which the body weight is converging. In a dynamic situation, this is of course much more moving than resulting from pure postural sway. The COP line therefore shows a temporal progression as well as its position in the overall pressure pattern. In the optimum case, the COP line runs as follows. In initial contact, the foot hits the ground in a slight inversion due to activity of the dorsiflexors. The COP thus arises slightly lateral to the center of the heel. However, due to the load-induced initiation of the physiological eversion movement of the heel, the COP immediately tilts medially to the center of the heel. The pressure pattern shows a pressure development originating from the heel center. During loading response, the COP line takes on a recognizable course into the direction of M3. The end of this phase is reached as soon as the anterior heel edge is reached. The expanding pressure in the heel area initially grows, but then subsides somewhat as the forefoot is lowered. In mid-stance, the COP maintains the direction taken and proceeds in a straight line towards M3 in the forefoot. In accordance with the lower ground reaction force, the longitudinal arch is clearly visible as a pressure zone, but does not show any pressure peaks. Later in mid-stance, a slightly expanding pressure peak appears at the lateral forefoot, which is medially oriented in its development. At about the anterior third of the midfoot, the COP begins to present terminal stance. At this stage, the COP line transitions to the metatarsal region and, analogous to the transfer of pressure from lateral to medial, now migrates towards the hallux. The maximum pressure migrates across the entire width of the anterior transverse arch from lateral to medial. In pre-swing, the COP is then transferred from the more medially located metatarsals to the hallux. The last measurable contact is generated by this. Many foot distortions that do not become apparent in a static situation can be detected much more precisely via the dynamic profile, since individual zones may be loaded more selectively over time. The last point mentioned as an example. If toes are also visible next to the hallux at the last moment of push-off, this can indicate relief of the hallux, for example in the case of an arthritic hallux rigidus. The red expanding pressure sign of a lowered longitudinal arch clearly appears in the mid-stance, which is the moment when the foot is completely lowered and the body's center of gravity is guided over the midfoot. A static image can only make this measurable in a much more pronounced form, as the pressure can be distributed over a larger support surface here. For this reason, a lowered transverse arch will also always appear more concise dynamically. The moment the body's center of gravity moves toward the forefoot and the pressure in the metatarsal area increases, the anterior transverse arch should fulfill a bridging function that guides the COP from lateral to medial. The splayfoot shows a much larger pressure region here, with no dynamics following the COP, eventually showing separate pressure zones below the metatarsals, each with pressure zones appearing separately, simultaneously, or in rapid succession. A flat foot appears with an evenly distributed pressure pattern and a distinctly widened midfoot. The COP line is relatively straight and possibly slightly faster across the midfoot region. The differential diagnosis between foot pronation and an elevated longitudinal arch has already been described in a video of a pedoscan dynamic. Here again as a recapitulation. In terms of a static pressure distribution, high arches and pronated feet have similar characteristics, which are primarily characterized by a less visible longitudinal arch in the midfoot. In statics, therefore, it is only possible to distinguish between the functionally very different foot types in a very clear situation. So, what do we expect in dynamics? The functionally characterized foot pronation often shows a completely inconspicuous heel position in the initial contact. As expected, the COP line runs centrally towards the third ray after initial loading of the lateral heel. The excessive eversion then occurs more often later in the course, like at the moment when the COP line leaves the area of the heel and passes into the midfoot. If we recall the course of the ground reaction force, this coincides with the first force maximum and the accompanying end of the loading response. From this point, the COP line turns medially, resulting in a shift of pressure development in the forefoot also to the medial. Increased eversion at this point has a significant compensatory function in mitigating the eccentric loading of the hip abductors at this stage, as it ensures that the transfer point of the ground reaction force is positioned closer under the body's center of gravity through medialization. It is often accompanied by tibial and/or femoral internal rotation as well as knee valgus. This pattern is quite common in the orthopedic context, but gets its name from neurology, where it is known as medial collapse. Now, what comes out loud and clear to the surface in neurology often shows only tentative tendencies in the orthopedic field. The internal rotation of the leg axis in a child with cerebral palsy is unmistakably more concise than the same but more silent pattern in a hip arthritis patient. The functional compensation principle is identical. Only the compensation is controlled from different starting points. Back to the differentiation. In contrast to the pronated foot, the high arch foot maintains a regular COP pattern. Over the missing pressure pattern of the midfoot, the COP continues in the direction of meta 3 without a visible turn towards the medial. The pressure development in the forefoot also runs regularly from lateral to medial. Differentiation should be possible without further ado, taking the above points into account. In order to better separate the different pressure zones, it is sometimes helpful to move the slider for the display threshold slightly to the left. This makes it easier to identify the foot zones that are subjected to higher loads. This page tells you about the course of the center of pressure decomposed down to atomic level of detail. The quantification reaches into very precise regions. Do not get lost in the pure number of parameters. In some cases, those detailed parameters are also important, but then maybe one or two, certainly not all. Setting this as a starting point, let's go through the contents of this page. In the upper left section, there's the so-called COP butterfly. It shows the course of the COP projected onto one spot. The lines forming the butterfly represent the progression of the COP between the left and the right feet. The vertically oriented sides are reached directly above the foot. They show the position and the course of the COP while the respective foot is in unilateral support. Since we assume a symmetrical gait pattern, we would expect the right and the left sides to be roughly equal in length, each starting about short of the heel and extending to the front third of the forefoot. A shortening of the vertical at the rear foot end would be caused by a forefoot gait. Often, however, we can also observe a shortening at the forefoot. For example, if the foot wants to avoid going into plantar flexion, the contralateral foot is lowered to the ground faster, so that a forceful ipsilateral contraction of the retrotibial muscles is avoided. In this case, the butterfly pattern will appear distinctly asymmetrical. In terms of values, this becomes interpretable with the average gait line length. The duration of the single support is also a reliable parameter for this, and the left-right relationship should point in roughly the same direction as for the gait line length. The diagonal parts of the butterfly represent a part of the gait cycle recorded in bipedal stance. Exact positioning of the COP is not possible, so the diagonal is always straight from the last monopedal COP position of one foot to the first monopedal COP of the other. Thus, for each step change, there are crossing points of the diagonals, which in the optimal case are always located at the same position. This gives you information about your patient's ability to walk across the treadmill in a relaxed movement pattern. Stronger coordination deficiencies would influence the gait line position anterior-posteriorly as well as laterally. These values indicate the deflection of the intersections of the COP butterfly. If possible, they should remain in the range lower than a centimeter. In the upper right section of the image, the focus is extended to the complete gait line, which results from the complete course of the COP under the foot sole during rollover, from the initial contact to the end of pre-swing. Analogous to the gait line length in monopedal, the complete gait line length should have a right-left symmetry. Shortening the gait line towards the rear foot would only make sense for a forefoot walker. To shorten the gait line ventrally would mean, for example, a premature lift-off of the forefoot due to a stiff ankle or hallux-based joint. Likewise, as previously described, the relationship of left and right stance phase durations should point into the same direction. Note, however, that you will always have to leave some room for variation. If the stance phase duration in a right-left comparison is only a few milliseconds apart, you should not necessarily derive a general tendency to symmetry. The distance covered has mainly an informative character. Depending on the treadmill speed, the distance covered is usually fixed. This value has no clinical significance. The track width calculates the lateral distance of the COP positions between the left and right initial contact. Usually, the value is in the range between 8 and 10 centimeters. A narrower track can occur, for example, with the Trendelenburg gait pattern. The narrow foot positioning moves the base of support closer below the body's center of gravity. This allows the ground traction force to be absorbed directly through the hip by the center of mass without the need for lateral stabilization. Of course, we are then talking about primarily bony stabilization, which bypasses weakened muscles but thus leads other compensatory muscles into overload or bony reactions like stiffness or a bruise. The COP deflection shows the lateral deflection of the gait line from its most medial position at the end of the pre-swing to the most lateral position either in the terminal stance, in the forefoot, or in the initial contact at the rear foot. Strong deflections do not really fit into a real gait pattern. Rather, the focus should be set into identifying very narrow deflections. The flat foot already mentioned, with a very straight gait line, will most likely present a correspondingly low value, which should be at the level of 10 to 15 mm at max. While the value indicates the average deflection, the complete time course of the COP deflection is visualized in the lower section. Here, the zigzagging back and forth motion of the COP can be seen in the context of the average deflection. One can check the consistency of the gait pattern over the measured period here. Optimally, each peak of the zigzag lies within the red and blue lines, with some variance always being allowed. However, if not a single line meets the actual average lines, an extremely unstable and wobbly gait pattern must be assumed. If this instability is not equally perceptible on solid ground, you should be cautious in a further interpretation of the gait parameters. Presumably, the patient then merely shows an exaggerated reaction to the treadmill effect. Possible gait deviations should then not be too representative. The Parameter tab sums up all important gait parameters and uses the internationally accepted wording so that even experienced gait analysts should be able to find their way around quickly. One note in advance. The values given on this page are mostly average values. Always pay attention to the information behind the plus minus. This value indicates the standard deviation as the average variance around the mean value. Again, we are talking about the reliability of the data displayed. Of course, a sample recorded as part of a 5-second synchronous measurement is much more effective for individual measurement outliers than those of a 20-second standalone measurement with pitter gait only. The page is divided into 3 areas, which initially allows a left-right comparison on many levels. Here, of course, we would first look for symmetry. The upper left area deals with the gait cycle. It is roughly divided into a stance and a swing phase, which together make up 100% of the gait cycle. In literature, an expectable relation of 62% stance phase and 38% swing phase is described. Simplified, this has been translated to a 60-40 ratio in a practical context. In this range, we would then also expect the data of a patient. The treadmill effect usually contributes to a moderate shortening of the swing phase, which then naturally lengthens the stance phase accordingly. If the stance phase is sometimes 63 or 64%, this is usually still within the acceptable range. However, if we are talking about a proportion of 70%, then this cannot be attributed solely to apparative effects. In this case, there is usually a functional abnormality visible. In addition, a longer stance phase does not necessarily have to result from a functional requirement of the prolongation of the ground contact, but from a restriction that requires a shortening of the swing phase. If the supporting leg's knee or hip cannot be sufficiently brought into extension, the swinging leg's foot would touch the ground prematurely. The swing phase is shortened and the stance phase is lengthened accordingly. The stance phase can be divided into the shock absorption phase, single support, and pre-swing using pedobarographic data. Load response is summed from the bipedally supported initial contact and loading response phases. Once the contralateral foot pushes off the ground, this phase ends. This should be within the first 10% of the gait cycle. However, prolongation of the stance phase could sometimes move the load response toward 12%, which still indicates physiological gait abilities. Prolongation beyond this is usually associated with a delay in the push-off of the swinging leg, either as a stabilizer function for the loading response of the supporting leg, or in the case of insufficient functional plantar flexion in pre-swing of the swinging leg. The single support represents the duration that the respective leg is unilaterally supported. Naturally, the value of one side is relatively identical to the proportion of the swing phase on the opposite side. A shortening of the single support is initiated when no force can be applied at its ends, either eccentric stability at the end of loading response or the concentric force of the plantar flexors at the end of the terminus stance. Accordingly, the durations of shock absorption and/or pre-swing would then be extended. In the lower left area, the rough foot areas and the proportion of the respective ground contact in relation to the total rollover are displayed. The rear foot usually contacts the ground with the initial contact and leaves the ground at about the midpoint of the terminus stance, which is after about 55% of the rolling motion. If the rear foot is on the ground longer, we can expect an insufficient plantar flexor group on that side. Shortening would be possible, thought analogously, due to hyperactivity of the plantar flexus. The midfoot is lowered during the early load response. The final contact of the midfoot occurs during the terminal stance, so that it is on the ground for about 70 to 75% of the contact time. The forefoot also touches the ground during the loading response and does not leave it until the end of the pre-swing. It thus comes to a value of about 92 to 93%. A foot slap or foot flat would increase this value up to 100%. Finally, in the right part, the gait parameters, which refer to the step development, are output. The single step length is a reliable parameter to measure the resulting gait symmetry. In a setting where the patient is walking on a treadmill during the measurement, it can be assumed that the step lengths are reasonably equal in natural comparison. This is the only way the patient can walk straight ahead on the moving belt. A step length difference of 6 or more centimeters is definitely a conspicuous sign. The absolute value is not really of great interest, since the total stride length is largely depending on the leg length. Thus, there are already inter-individual differences in connection with the body size. In adult humans, a step length of more than 35 centimeters can be assumed. In principle, the step length results from the distance covered by the swing leg. In a pedobarography, the value for one side results from the spatial span between the end of the ipsilateral pre-swing and the moment directly before the initial contact of the same leg. Analogously, the step time should give a similar relationship. This also depends in its absolute expression on the leg length and the treadmill speed, but in principle, a duration in the range between 600 and 800 milliseconds should be possible. A strong lateral difference in step length and duration can result, for example, from insufficient hip extension or plantar flexion when the supporting leg is moved backwards during rollover. An acute muscle fiber tear in the right gastroc would cause the patient to avoid forceful plantar flexion on that side. However, dorsiflexion when the heel then remains on the ground in terminal stance is also painful, as the structures get stretched. Therefore, the left swing leg is then brought to the ground earlier, which then shortens the left step length and time accordingly. Of course, the stride can also be shortened if the hip cannot move sufficiently into flexion in the swing, or if the knee has problems to move from maximum flexion in the mid-swing back to extension. The stride parameters result from the sum of the average single step data. In this sum, it is quite acceptable if the values are slightly below the specified normative range. This can be caused by walking on a treadmill. A stride length of 120 centimeters is therefore not necessarily conspicuous just because the value is about 20 centimeters below the norm. However, if this is the initial value and your patient provides a higher value in a later control measurement, then you can possibly attribute the gain in function directly to your treatment approach. The track width has already been described, so continue with the foot rotation. What is relatively easy to determine in statics with a stable footprint becomes a somewhat more complex calculation step when the rotation is to be taken from a dynamic profile. For this reason, this value is the only one that is not averaged over all steps but gives the rotation of the respective mean representative alone. This value can be edited in the processing of a pedogate measurement as part of the segmentation by manually placing the longitudinal axis of the foot from the center of the heel to the interdigital area between the second and the third toe if needed. Very straight aligned feet often prevent sufficient dynamics in roll-off. In this case, a relatively small COP deflection should be indicated in the COP gateline tab. In many cases, however, we will find an increased rotation instead. This has the compensatory ulterior motive of increasing the support surface as quickly as possible after heel strike. If the foot is in neutral alignment, this takes a little longer because the foot levers over its entire longitudinal axis. If, on the other hand, the foot is externally rotated, it becomes shorter towards the direction of motion, so that the full base of support is on the ground much sooner and establishes stability there. The cadence is commonly assumed to be a global parameter influenced by the outcome of all present gait restrictions. In case of insufficient muscular or coordinative capacities, the number of steps that can be taken within 1 minute is reduced. In the neurological field, it is not uncommon to observe cadences lower than 50 steps per minute. But beware, in a treadmill situation, the set treadmill pace also has a major impact on cadence. One tends to set the treadmill pace slower rather than faster for safety reasons. It is fine to keep it that way to give your patient some time to get used to the situation. In the final stage, however, you should make sure that the patient walks over the treadmill in a fluid motion as discussed in advance. If the patient walks too slowly and not at an individually comfortable pace, the cadence will surely decrease as well. Again, however, a before and after comparison is always a good idea. If your patient tolerates a higher treadmill pace in the after measurement due to a good response to the therapeutic intervention, the higher cadence can certainly reflect the gain in function well. Cadence as a global landmark about gait ability is widely used to infer quality in the management of daily life functions. A patient with a cadence of only 60 steps per minute will find it much more difficult to descend 4 stories to go to the bakery across the street. He may not even be able to reach a supermarket 350 meters away. However, if we manage to increase the cadence to 90 steps per minute with our therapy, the patient will still present himself well below the norm. However, it will be much easier for him to cope with the scenarios presented in his everyday life. This will then also have a positive effect on the overall quality of life. The parameters gait line way, speed, and examination time are purely informative. Here you can check again how fast the treadmill was set, how long the measurement lasted, and which walking distance results from it. This tab offers a very detailed representation of the segmental load distribution during rollover. The 10 foot zones are divided into the following areas. The rear foot for medial in light green and lateral in dark purple, midfoot in green, metatarsals 1 to 5, in yellow for M1, light blue for M2, pink for M3, brown for M4 and red for M5. In the toe area with the hallux in blue and the remaining toes in purple. The display consists of a reference to the automatically determined mean steps. At the side edges, you can see the duration with which the respective foot zones have measurably touched the ground. At the top center, the foot zone segmentation on which the display and parameter calculation is based on can be derived. Please note that the accuracy of the determination of the foot zones from a dynamic process is relatively difficult and depends to a large extent on the gait behavior of the patient. For this reason, you have the option in the samples processing to refine the segmentation based on your expertise. Your adjustment will then be fully incorporated into this presentation of results. The graphs shown below represent the time course of the force development under the foot segments. The color coding here corresponds to what already has been mentioned. The basic structure of this page is the same as the previous result page for the foot area's contact times. However, the focus on this page is on the actual vertical forces absorbed. These force developments in the temporal context provide once again a very detailed insight into the segmental involvement in the weight transfer and forward movement. In the area of the metatarsal, for example, it can be expected that the force application already starts in the loading response and describes a transfer from lateral to medial. Following this idea, the temporal sequence would show first the red, then the brown, the pink, the light blue, and at last the yellow force curve coming into use. However, an already mildly pronating foot would already build up another sequence. Here, we would clearly see how the first segmental force increase does not begin on meta 4 or 5, but on M3, 2, or even M1. I truly hope this tutorial was able to provide you with new information and maybe some ideas on how to make best use of a DIERS product. If you liked this tutorial, we would be happy to see you also tune in into the other training videos. Stay tuned!